null hypothesis that f is equal to g, and testing is this distribution the same as this distribution? If that's what you want to test, then use the median test. But if you want to test something weaker, like is the median of f equal to the median of g? You're testing more than you need to then, and you might have higher power to use a bootstrap. But then again, you're giving something up to use a bootstrap and passive product procedure. It's not a finite sample, it's not exact. There's a trade-off there. Okay, so maybe we'll before we'll skip the implementation test. And let's talk about something which isn't in the notes, and which I mentioned at the end of last day, which is supposed to be doing predictions. And we'd like to have some notion of uncertainty about prediction. It's great to say, I'm guessing this, I'm guessing this outcome, but maybe you want some sort of prediction confidence. Now, I'm not suggesting you always want that. Sometimes you really just want to get it. But there are cases where you'd like to have some sort of notion of confidence. And one way of doing that, and it's not the only way, but one way is to use what's called the formal method. This is an interesting method due to Vladimir Vogt. Vogt is an interesting guy. He's a Russian guy who lives in London. His advisor was Kolmogorov, the guy who invented probability theory. And a lot of his work is very, very foundational about the foundations of probability. And he's got a book about this. Now, unfortunately, he tends to see things sort of the entire edifice of probability he sees from a certain point of view, which has to do with sequential prediction. In fact, in some sense, a lot of the online learning stuff that you may have come across has roots going back to Vogt's work. So when you look at his work, it's sometimes very hard to read because he has different language and different terminology and different definitions. And in fact, the way I'm going to describe the stuff today is quite different than the way you describe it. But the idea goes back to him. The way I'm going to describe it is much more statistical. In fact, I have a paper with my colleagues, Jim Lee, Jamie Robbins, and me, which is like there's two papers, I think 2012, 2013, which is basically taking Vogt's idea and making it more statistical. So if you want to read about it, you're probably better off going to our papers first because it would be in language you're more familiar with. And then you look back at Vogt's papers. And the basic idea is actually really, really simple. It's a very simple idea and very powerful. So it works for both regression, it works for classification, it even works for the unsupervised. So let's start with, I think the easiest case to start with is regression. So we have the usual regression set up. And we've got our pairs of data. And now we get a new observation, and we'd like to predict this stuff. But the goal here is a little bit different. We actually want something like a confidence set. I want to give you not just a prediction, but a confidence set for that. And I want that confidence set to track the true y with probability like 95%. But this method, as we'll see, turns out to be, it's not asymptotic, it's finite sample, so it's not going to be approximately 1 out of something, it's going to be at least 1 out of something. And it's distribution free. So here's the cool thing. No matter what regression method you use, linear regression, lasso, non-conventional regression, this is still going to cover the true y with this guaranteed probability. That's kind of amazing thing. How can that happen? Well, let's talk about the method, and then we'll say how it's working. So I want to guess. I want to guess or predict, as usual, y and plus 1. So we'll assume that you're going to be using some sort of regression thing, m hat of x. Again, it could be linear. It could be something sparse. It could be non-parametric. We're going to be very agnostic But what it is, all I'm going to think about it is it's, you input some data, training data, and out comes your MHAT, your regression. And there's no assumption about what that is. Now the method works like this. I'm trying to figure out what is y n plus 1. So let's assume y is real value, just to keep it simple, although that's not even the same yet. Let's pick a value, an arbitrary value of y n plus 1. Let's set y plus 1 equal to some number, small y. Right now, that's just an arbitrary guess. It's just a number, 1.2. Okay? And let's proceed as if that's the right answer. Somehow magically, just. Okay? So what you do is you form the augmented data set. So tentatively assuming I've guessed correctly, I can now fill in the n plus 1 data point. Right? This is now a data set of n plus 1, where this point has been set equal to little y. I know it seems kind of weird, but just pretend the guess is correct. Now you have the data. Now you have to compute your regressor, but you have to use all n plus 1 data points. So let me call this m hat sub y to remind us that we've augmented the data. Okay, so now we take the augmented data with this extra guess in there. We recompute our regressor, whatever this is. Now you compute some statistic. And the other interesting thing about this is it can be any statistic you want. For concreteness, I'm going to use the following statistic. I'm going to use the residual, which is yi. So I'm just taking the ith observation, comparing it to its predicted value. But now, don't forget, I have n plus 1 of these, right? I have R1, R2, all the way up to Rn plus 1. So let's think of these numbers here. Suppose, well, the way I did it, these are positive, right? So maybe it looks like this. Okay. Let's consider testing a hypothesis now. I want to test the null hypothesis that the unknown future observation is exactly equal to 1. Let's assume that the null hypothesis is true for the moment, and say, under the null hypothesis, when I look at these residuals, so this could be R1, this could be R2, so these are just all the residuals I've computed. One of them is going to correspond to this guy, Rn plus 1, to the guess. Maybe it's, I don't know, maybe it's here. Now, if you think about it, the ordering of the data doesn't matter. These are RID. Under the null hypothesis that yn plus 1 is equal to y, I actually have n plus 1 draws to the distribution. They're exchangeable, as we say. That is, the ordering doesn't matter. And also, I hope it's intuitively obvious that the ordering of the residuals is uniform. That is, if I ask you ahead of time, where's the third residual going to come out? What's the rank of the third residual? They're all going to be equally likely. Sam?
Just to be clear, is that hat or enhanced by this?
Pardon me?
The residual given over there is enhanced or enhanced by?
That's why I have.
So it's enhanced using the augmented data set?
Yeah, oh, I see. Yes, thank you. Thanks, yeah. It wouldn't work otherwise. That's great. Right, so in other words, the ranks of the residuals are uniformly distributed. If you just forget about this, and I told you I'm doing regression and compute these size of the residuals, what's the chance that my first observation happened to come the biggest rank, or this one, but because the data are invariant in the permutations, every rank is equally likely. There's no reason why the first data point from random data would be the biggest one or the smallest one. So these ranks are equally likely, and in particular, this one, because it's a draw from the same distribution, it's just as likely to be here as it is here as it is here. Does that make sense? There's no reason why we can go one place or another. In particular, of course, if I had a bad guess of little y, the null hypothesis was false, it might have a unique result. But right now we're computing this under the null hypothesis. So in fact, I'm going to compute the p-value, which I'm going to define to be just the number of observations, proportion of observations to the right of this guy. So the p-value, let's call it p of y, just the count. This is a lot like a permutation test in a sense. We're just counting. Although we're not doing permutations, but we're using the same kind of idea. We're just counting how often something happens. In particular, how many of these residuals are bigger than or equal to the guess I made. And the point again is, under the null hypothesis, if I guessed correctly, these are all equally likely. This p-value is uniform. Actually, it's kind of a discrete uniform because it can only take value 1 over n plus 1, 2 over n plus 1, 3 over n plus 1. But let's ignore the discreteness. It's basically uniform 0, 1. In fact, it turns out the discreteness makes it conservative, so it makes, if anything, it actually reduces the chance of a false positive, but we'll just think of it as being uniform. It's actually sub-uniform. So under the null hypothesis, this is the uniform. Now, in 705, I should have checked this first. Did you talk about inverting tests to get confidence set? Yes. So you know, if I want to get a confidence set for theta, let's just spend a minute reviewing that. One way to get a confidence set for a parameter theta was to test theta equals to theta 0. And do that for every possible value of theta 0. And what you saw in 705 was it's a one-line proof that if I now collect together all the ones that I didn't reject, that's called inverting the test, that gives you a valid confidence set. So if this is all the possible values, say theta 0, and if you think of saying, I accept or reject the null hypothesis. So this is reject, accept, reject. You have to imagine that every possible value is a null hypothesis test. And if you collected together all the theta knots that were not rejected, what you proved, and again it's a one-line proof, was that this gives you a confidence set, that the probability that C traps the truth is 1 minus alpha. Hopefully you remember that. If you don't, well, trust me, that's true. You just test every possible parameter value. If it's rejected, throw it away. If you didn't reject it, keep it. That forms a confidence set, a valid confidence set. And we do exactly the same thing here. We have a p-value for every possible y. We're taking every real number y and testing, is that the unknown y? And either we get a small p-value or we don't. So what we do now is we form the confidence set, a set of all y's, such that the p-value is big, so that we don't reject it. And because this has exactly a uniform distribution, actually uniform discrete distribution, but uniform distribution, there's no approximation problem. That's basic probability theory. It follows that the probability that this very simple idea. Find an example. Now you might think this is computationally expensive because I have to take every possible real number, throw it in here, recompute my estimator. But you can, as you can imagine, there are lots of little computational tricks you can do to speed these things up. For example, huge values you know are going to be rejected. And oftentimes when you take an estimator and you augment it with one more point, there's a simple update formula to compute the estimator or even to approximate it. So there's lots of quick approximations you can do to make this very fast. In fact, in our papers, we talk about this tricks you can do. So it's not as computationally as expensive as it sounds. In fact, it's very complicated to simulate classes. So the method, again, is just guess a value, and you're really just testing. Is that the t-value to do a test? And you just keep all the ones that don't get rejected. And that gives you a valid prediction step. This is a prediction step, right? This is confidence set for the prediction step. Yeah.
So what are we assuming about the regression of the
So that's an interesting question. What are we assuming here? We're assuming the data are IID from some unknown distribution. That is the only assumption required to get a valid confidence set. Now that might seem too good to be true, right? But here's an interesting thing. So what happens is this, is what if I'm making a terrible assumption? What if I'm using linear regression? That's my unhappy. Suppose it isn't linear. We must pay a price somewhere, and you do. It turns out the only way this set can track the true value 95% of the time when you're using a regression model which is far from the truth is to be big. And you'll find this happens automatically, is that if you pick a regression model, which is a terrible model, you will get a huge confidence set. But it's almost like a kind of a diagnostic. If you're getting a huge confidence set out of this, that's telling you something about the law. It's telling you the law is wrong. In fact, an interesting exercise to do is to do this with let's say do non-parametric regression, let's say with a bandwidth or a tuning parameter h, and let's fix an x, fix the new x, and plot and do this procedure, we get an interval. So for each x, imagine for each choice of bandwidth, I run this procedure. I'll get a different interval. What ends up happening is the intervals look like this. So this is y, and I'm drawing the prediction interval as a function of h. It looks like this. So what's happening is if you take a good bandwidth, you get a narrow interval. But if you either underfit or overfit, underfit or overfit, you still have validity. That is, this will still contain the truth with probability 0.95, but you won't get efficiency. You won't get a narrow interval that you're widening. In fact, the papers that I wrote, that's what that's about actually, is the connection to statistical efficiency. So the fact that it works even if you're using a terrible model is actually, there's no logical contradiction there, but you won't necessarily get a good prediction. You might get a huge prediction. So one of the intriguing ideas, and this is also something in our paper, is that you can use this as a way to do model selection. You can use this, for example, as a way to pick the bandwidth. You have to be a bit careful though, because now you've changed the coverage probabilities because you're doing many of them. You have multiple testing intervals, so you have to do a kind of adjustment for that. But that's a small thing. But yes, it is a way to actually choose models. In fact, one of the intriguing ideas that I keep needing to do, but when I read around to was, for example, the lasso and things like that. It's a way to choose.
Maybe a sort of similar question. Does this at all make sense to use in like a binary classification setting?
I'm
like
going to do that next.
Oh, like active learning or something?
Yeah,
okay,
yeah,
cool.
absolutely.
Very
Yeah.
cool. Yeah.
Just to be clear again, do the samples need to be independent or identical?
They actually need to be exchangeable, which is weaker than any of those, but usually, I mean, IID implies exchangeable. If they're independent but not identically distributed, that probably won't work.
Because the noise is dependent on.
Well, no, I'm making the usual assumption here, which is simply that the pairs are drawn from some unknown distribution. That's it. That's the only assumption. So the only assumption we're making is that pairs, x1, y1, x, and yn, are a draw from some distribution. That's the only assumption. In fact, you can weaken that again to what's called exchangeability, which is slightly weaker, but IID is usually what we assume. So I'm not making anything stronger than we usually assume. So yeah, this is a pretty cool thing. I wish it was more popular. It's very simple and powerful, and I think why hasn't it caught on? And I think part of the reason is, again, I think Volk tends to write in a slightly different language, that mathematical language that most people in machine learning and statistics are used to. So I think maybe you just don't quite understand what he's doing, but it's actually works very well, and it's a very useful thing. This is assuming you want a prediction interval, right? I mean, maybe you just care about the best prediction and you don't care about that. But if you do want some kind of confidence set for your prediction, then this is an easy way to do it. And yes, let me tell you now how to do it for classification. So in this case, so what ends up happening here is kind of interesting. We do it exactly the same way, except we have to come up with some sort of score, some sort of meaningful score. By the way, you might ask, what if I've chosen a different score? You would still get a valid region, but again, different scores might give you narrower regions than other ones. That's an efficiency question. But in terms of validity, by which I mean that you cover the true value of probably one myself, but that's not effective on certain choices. So in classification, how do you choose the score? It's going to depend on what classifier you use. Maybe you're using nearest neighbors, or you might use the distance to the nearest neighbor or something. So just to have a concrete example, let's suppose we're using logistic regression. Again, this will work with any classifier, okay? But I'm going to do logistic regression as an example. So remember, the model is that the probability is something like e to the beta transpose xi. So what you need to make up some sort of residual or some sort of score, and so a natural one here might be this. Yi minus Yi hat, right? Once you have a beta hat, you get a predicted probability, and you could just use, this is going to be either, oh, maybe I should have done 0, 1 here. 0, 1. So this is going to be 0, 0 or 1, and this is going to be a number between 0 and 1. That would be a perfectly fine score. But now, what hypothesis tests do I have to do? In the regression case, Y could have been any real number. Here it's a bit easier, because Y, you only have to test that Y is equal to 0 and Y is equal to 1. And again, you'll either end up, what's going to end up happening, it turns out, is you could reject one, you could reject both, but you might end up accepting both. Right? You're going to get a p-value here and a p-value here, and you're going to keep the ones that are bigger than 0.05. So sometimes what will happen is you get something like this. Sometimes you get this. And let's think about what that means. I'm giving you a random set, C, and I'm claiming that that's going to contain the true Y with probability at least 95%. So think of it as a game. We do this, I give the C, now you give the Y, and I'm claiming that will track 95% of the time. But sometimes the price we're paying here for getting this extra information, for getting this uncertainty, is this. Sometimes you're going to claim, all I can say is it's 0, 1, which is not very informative. But it is informative in a way, because it's telling you that's hard to classify. So this is, we call this the ambiguity. So the ambiguity here will be usually pretty small, unless you have a lot of difficult cases. Think about classification problems where you happen to have a lot of operations near the decision boundary. Then you're going to get a high ambiguity. You're going to get a lot of ambiguous classifications. So that's just telling me you have a lot of difficult cases to classify. So whether you consider that a good thing or a bad thing, I guess depends on how you look at looking at it. If you wanted to get out a definite answer, that's disappointing. But if you want to flag the fact that there are some difficult cases, this is a useful thing. But this also has another issue, which is, again, if the logistic regression model is a bad fit, then the only way it's going to track the predictions with high probability is to output this a lot. So when this is happening a lot, it can happen because you have a lot of observations near the decision boundary, or because your model is bad. And an interesting research project that somebody should look into is developing the bank further. You know, it shouldn't be too hard to develop diagnostics to tell you when you're in which situation or the other. So using this as kind of a diagnostic is an idea that's kind of lying around out there, but nobody has investigated in great detail. But that's it. So this is even simpler than the regression case. This is actually the case Volk emphasizes. Almost most of his papers are about classification.
Sorry, is this with a set alpha, or can you figure out like?
This will give you a prediction interval for each alpha, in fact.
So can you figure out the value of alpha where you switch from an ambiguous?
Yes, you can. That's a good point. So you could ask, you can do this for every alpha. And you can get something like, I don't know, a p-value, I don't know what to call it. At what alpha level does it finally jump from being a definite prediction to a set? And then you can say that's, you know, that level of alpha is telling you something about how uncertain this is. Okay. Any other questions?
But is there something you couldn't do this way?
Is there anything you can't do this way? Well, it's only good for prediction, right? We can get parameter confidence intervals for parameters. It's only a predictor. Right? So,
But if you can do model selection.
yeah, but let's suppose we want to estimate the mean of distribution. There's nothing how to do confidence intervals, something like that. So it is a general tool, but it is very predictable. In fact, you can also do, as I'm going to explain now, here's the unsupervised case. And again, this was something we did in our paper, but again, really building on Vo's work, which is, suppose you have y, 1 to y, and there's no x. But you can still say, well, how do I predict y equals 1? You do the same procedure. Throw in an augmentation, but now what does it mean to do some sort of, you know, measure of fit or residual? Well, you use density estimation. So what we did, and this turns out to be under certain conditions actually optimal, is we define something like a residual. It's not really a residual anymore. To be 1 over density estimation. So it acts like a residual, because if you take an extreme value way out there, the density will be small, you have a big residual. So it is sort of like a and now you do exactly the same thing. All you do is you test again y equals 1 equals y for every y. The procedure is exactly the same now. It doesn't. The fact that there aren't any x's doesn't matter. I have n observations, I augment it, I compute a score, I invert the test from the p-value, and you get a prediction. So what you're going to get, in general, let's say y is a vector, you're going to get some possibly weird region in space, but it will have the desired property that again, it's not saying, it's not a confidence of the density estimate, though, right? We're not getting any sort of confidence band or anything like that. It's just a predictive estimate. So it's a little bit more modest in terms of the confidence stats or confidence intervals, only about prediction. Although, from the point of view of machine learning, of course, prediction is often considered the most important thing. And it does solve that problem in the sense of providing a distribution-free confidence set.
Just to be clear, so like you could have sampled y and plus 1 from here of y and
No. Y equals 1 is future unknown observation. So
But
you
what if I sample my y equals 1 from P and y I? Is that, is it distinct?
No, they all have to be, we're assuming, the way to think about it is I have n plus 1 observations for some distribution P, but I haven't shown you P yet. I've only shown you the first n, and you're trying to guess the next one. You're just trying to guess the future observation.
So is my interpretation of the regression setting, which is like you have n data points, you train something, and if you want to predict at another point, you estimate using the prediction and then perform this test. Is that logic?
Yeah, think about it this way. I have n people, I do the regression. Now I measure that person's blood pressure, I want to predict their Y, I do this procedure, and outcomes my prediction.
So in the register regression case, I just do the regression on just the x1 to xn points, and then I can get a prediction for n plus 1, right? And that's a probability. And if I do this procedure, and I look for alpha, which is suited to the negative set, for like either the confidence interval either be 0 or 1, then that sort of also gives you a probability of like how confident I am that it's that value. Are those related anymore?
I think what you just said would probably be an asymptotic approximation to this. And keep it, yeah, because one thing I want to keep in mind is don't forget, when we compute this from this, it's from the augmented data. That's the difference, I think, what you're saying. It needs to be recomputed every time. It's modulo computation matrix.
Sorry, just changing the residual slash score have any kind of, I don't know if you use, for instance, log loss or something like that?
Absolutely, you can use any score you want, and so this hasn't been investigated much. It still gives a value, but under certain conditions, one score might be more efficient than another,
Sure.
meaning the expected size of the set length score. So there's a lot of interesting open research questions. So when is one particular score going to give you a smaller expected set than another one? It would be a very interesting project for someone to do this on. Yeah, you could even, if you're really fast, you could figure it out and submit it to NIPS by June. The whole 2 weeks away or 3 weeks away. No, month and a half, but you got it done. Yeah, that was also one of the reasons why I wanted to mention this, because I think there's a lot of interesting open research questions that haven't been addressed.
If you don't assume that the data are IID, but you know the sequence or something like that, you also
Another interesting question. So what if the data aren't IID? Well, one thing I should say is, of course, everything you've learned in 701, 705 in this class have assumed the data are IID. Right? And so once you leave the IID world, you're in a world of pain. But it depends, right? So if it's a time series situation, there are techniques for trying to deal with the correlation from the time series, yada, yada, yada. So depending on the departure from IID, I'm sure it would be possible to make adjustments to this and make it work, or at least make it work approximately. But again, it's not enough. Any other questions? Okay, good. I hope I whetted your appetite about that. Now let's talk about another one. Okay. Let's see. How about this one? Yeah. This is a little bit off topic, but since I'm on to the finite sample rule, I thought I'd just mention one other point. There are other situations where we can do finite sample confidence regions, even in high dimensions, with no asymptotics. So I just wanted to give you an example of that. I don't know if you did use the finite sample confidence interval for the median for quantiles and so on. Maybe you didn't remember it, I can tell you. So I'm going to show you how to do a high dimensional confidence set for a whole string of medians. Good finite sample. And it's using a very simple trick, and it's using a little bit of concentration to measure. And it's a very cool trick that everybody should know. It's a really, really nice. I should put all these little gems together. Think little tricks everybody should know. This is one of those. Because I'm always surprised to find out that a lot of statisticians even don't know this little trick. I learned this like when I was an undergraduate. Maybe it was because in the old days, in those days, you know, you did a lot more kind of modest stuff with 10 observations as well. This stuff is very popular. And nowadays, this seems kind of uninteresting or something, but I think it's actually pretty useful. So let's suppose if you want to estimate the mean of the distribution, we know how to do that, x bar. If you want to get a confidence interval, really the only way to get a confidence interval for a mean without a lot of assumptions is something like either central over here or a bootstrap. But if we're instead willing to estimate the median, and that's a perfectly reasonable way to measure some notion of the center of distribution, we can actually get a finite sample confidence interval very easily using a trick plus concentration measure, and then it extends immediately to high dimension distribution. So here's the deal. We have an arbitrary distribution. Look, I'm going to actually assume that it's the median is well defined, but that's actually not even necessary. What I mean here is that the median is f inverse of a half. Sometimes if there's a flat spot there, you have to decide what you mean by the median and so on. That's a small technical point. Let's just assume there's no flat spot. So yeah, just to avoid this. And I want to estimate the median. So the obvious thing to do is, well, the sample median of the data is actually a consistent estimator. In fact, working out these limiting distributions of the median, however, I don't know if you did it out yet, it's not trivial. That's not a trivial exercise. But I want to do something different. I want to just get a confidence interval. And here's what we do. First of all, you form the order statistics. Remember, the order statistics are just the data written out in order. We usually use this notation, right? The bracket means they've been ordered. So here's x1. Okay, now I'm going to pick an integer k. And in a minute, I'll tell you exactly how to pick k. But for the moment, it's just some integer, let's say 5. And you come in from the left, you go 1, 2, up to k on this side. And you do the same from the other side. I have a feeling that maybe that's n minus k plus 1. It's either n minus k or n minus k plus 1. Let's not worry about that. This, I'm going to compute this interval. And the first thing is that I'm going to show you how to pick k in such a way that that's guaranteed to that interval between those two order statistics. No matter what the distribution is, the probability that the median is in that set is at least 1 minus L. For all distributions. In fact, a lot of these things I should probably write just to make it clear. Even if you take the input of every distribution function. So there's no asymptotic approximation. There's no distributional assumption. When this holds, we often call these things distribution free. It doesn't matter what the distribution is. So let's prove that. It's going to use it's a very short proof. I'm going to introduce the following random variable. Let me draw again a real line. Here's the true median. Let's suppose that's the true median. There's some data. Define V to be the number of data points less than or equal to mean. Now B is kind of a weird random variable. It's a random variable, we don't know what it is because to compute the, you have to know data. We don't know data. Nonetheless, it's a well-defined number. There's some number of observations less than or equal to the median. Question. So here's the median. B is just this count. What is the distribution of B? Close. I'm just counting how many observations succeed in being less than theta. I'll have to say the word success. Yes, it's either a success or a failure. Success means it was less than theta. Failure means it was very big. So it's just binomial. It's exactly binomial. But what is the probability? Half. Beautiful. That's a nice thing. I know that distribution. We know those. So now let's look at our confidence interval. Let's look at the event that we successfully tracked theta. The event that we tracked theta, that's the event that xk is less than theta, which is less than x minus 1. But that's identically equal to that k is less than b, less than 16 minus k. Because, why is that? Because, let's see, for k observations, if the kth order statistic is less than theta, then that means the number of observations your b has to be at least k. And similarly, the other way. For theta, for the n minus k, if the n minus k order statistic is bigger than theta, then the number of failures is at least, did I get that? I might have to modify this. You might get it. I think there should be a plus 1 there. It's not where plus 1 there. I think there's a plus 1. This is beautiful now because I've just taken this, which looks hard, covered with something, just take it as binomial. And there's no parameters left. So the probability that this doesn't work, the probability that theta is not in the confidence interval, is it's the tail. It's the probability that theta is less than k plus the probability that it's bigger than that. Which is, let's just do one of the two tails. Let's say it's 2 times the probability that b is less than k. And now you can see what I'm going to use scoping inequality because this is 2 times, I'm just going to divide by n, subtract the mean. And I hope you recognize this. This is just like, coin flipping. Probably that you deviate by more than epsilon, or epsilon. We know from Hoofting's inequality that that's less than or equal to 2n epsilon squared, where epsilon is. So we use a little bit of concentration of measure. And I want this to be alpha L over 2. Alpha. If that's alpha, then the probability that we failed is at most alpha, so we have coverage 1 minus alpha. So now we solve for k, so let's tell you the answer. K is n over 2 minus n over 2 log. So there's, again, something that's been known since the 30s that's been lost somehow. It's very difficult to notice, but it's really simple and really useful. To review, I just order the data. I find the kth order statistic, where k is given by exactly the formula, and then I find the corresponding right upper order statistic, that's just these 2 order statistics, and that's it. And you can try this, generate data from the weirdest distribution in the world you want, doesn't matter, and you write some code and repeat it, and you'll see you do trap the median 95% of the time. And the beautiful thing is now suppose I want to go high dimensional. Suppose I have a high dimensional vector, and we talked about how to do the bootstrap for the high dimensional mean. We can do the same thing for median. So I have, each data point now looks like this. It's a vector length d with corresponding set of medians. And I want to make a confidence rectangle again, or this one really will be a rectangle, that simultaneously traps all the medians with probability 1 minus 1. Well, you do exactly the same argument and you take a union bound, and what's going to happen is d is going to go right here. When we sum, you know, take a union bound, we replace it with a sum, you get 2 times d times this. And nothing's going to follow. And when you solve, the only thing that changes is it enters logarithmic. A is n over 2. That's it. You now do this separately on each coordinate. So even though we're going to use the same order statistic for each variable, the width of each one will be different, right? Because where the kth order statistic is for the first feature and the second feature and the third feature could be very different. But you will get a rectangle, and the probability that the whole vector of medians is contained in that rectangle . And the nice thing about that, again, is we're not making any distributional assumptions, and we're also not making any asymptotic approximations. So that's a little bit off topic, because I don't know how often we're going to want to estimate a high-dimensional median, but I wanted to really get across the idea that we can do, you know, anything without all of these order simple approximations. Okay, next. In our bag of tricks. Any questions, though? Now, let's see. Which one is going to do? What he's going to do, I was planning next on doing an extension of the bootstrap. Or I could do subsampling. Would that mean anything to anybody? Somebody actually ever do anything? Subsampling. Somebody wants to see subsampling? Which you've heard of it. I'm either going to do the relationship. I wanted to do. I talked about the extension of the bootstrap. Deal with uncountably many parameters and how it relates to stuff around the concentration method. Or something called subsampling, which is an extension of the bootstrap. I heard one vote for subsampling. I don't know if anybody else has it.
Have you been doing stability stuff?
What's that?
And for subsampling, have you been doing stuff about stability? Or?
No, it's just a different way of getting confidence intervals. I need to flip a coin. Depends whether you want to see kind of more method or more theory. Subsampling, okay. Think of that. Yeah. I'll tell you, in case I don't get to it, that cover numbers and all that stuff relate to bootstrapping and whatever. But let's talk about subsampling. I didn't prepare notes for subsampling, so I'm going to do it out of my head, which has some risks. You might want to write in pencil, not in pen. So subsampling is a kind of modified bootstrapping, and people use it in cases where the bootstrap fails. So you're going to do in the homework an example where the bootstrap fails. There are cases where it fails. And it's also used in what might be called difficult cases where the bootstrap, remember when we proved that word, we were really relying on kind of Gaussian asymptotics. But there's lots of more kind of bizarre, difficult situations where things don't necessarily converge very well. And so it's not clear what you should do to get confidence intervals. So subsampling was invented to deal with this. Okay? It tends to give slightly wider intervals, but it works under extremely weak conditions. So here's how it works. And by the way, the proof that it works is interesting because it's much, much simpler than the proof that bootstrap works. So it works like this. X1 to X1. And again, I have some quantity, let's say beta hat. We're trying to estimate the quantity of data. I don't want to get a confidence interval. Let's suppose that, let's start by supposing theta hat minus theta converges to some distribution, but we don't know what it is. It might be some weird thing. In fact, one of the things about subsampling is you don't even have to have root-n convergence. It could be converging at some weird rate. It's usually true that if you multiply by something, like n to some power or log or something, it will converge to some distribution. It doesn't have to be root-n. In fact, there's a version of subsampling where you don't even have to know the rate. You can actually figure out the rate from the method. But to keep it simple, let's suppose it does converge at a root-n rate. But it's not necessary. So we have root-n, they converge to some distribution L. We don't know what L is. It's not normal. Maybe it's involving thresholding or things like that. But that's constructed properties. Bootstrapping may not work. So subsampling, you do the following thing. We're going to choose a number b, which depends on n. It's an integer. And for now, we're only going to require two conditions. It's going to grow with n, but it's smaller than n. So think of n to some power, n to the 3/4 or something. And now what we do, remember in the bootstrap we sampled from the empirical distribution. That's not what we're going to do here. We're going to draw a subsample of size b, which is smaller than n, without replacement. Okay, so I'm going to, let's suppose b is 5, n is 100. I'm going to draw 5 observations at random. So a subsample, I'm going to draw a subsample of size b. Let's call the first subsample S1. Now, let's think about this. How many subsamples are there? How many possible subsamples are there? N choose B is a good number. Fortunately, it turns out you can prove that you don't have to take all possible subsamples. It suffices to randomly choose some number of subsamples, like 1,000. So in practice, we draw a subsample, put it back, and repeat 1,000. For the theory, we're going to pretend that we actually have all the subsamples just to make it simpler. So I'm going to pretend I have all possible subsamples. So imagine, again, I've taken all n choose b, there's going to be a large number of possible subsamples. Notice an interesting thing about each subsample. Let's look at one of these subsamples. That's b observations. You can think of that as randomly drawing b observations from the tree distribution. It's not a draw from the empirical. If I take 1,000 observations and just give you the first 5, you now have a real sample size 5 from the tree distribution. So each of these is a sample size b from the tree distribution. And now what we do is we take each subsample and we compute our estimator. So this is beta hat 1, beta hat n. And what we do again is we form an empirical distribution, but this time it looks like this. So it's called alpha 2. sample size B. More generally, it would be whatever the appropriate rate of convergence is. This is the subsample, and this is the original sample. So it's very much like a bootstrap. Look at this. And we're going to find the quantile here. Let's say that's T, so that's the 1 minus of the quantile. And now our confidence interval, though, even though these were computed using root E, the confidence interval is just theta naught plus or minus T over root N. So it's really just like bootstrapping, except we're drawing subsamples of smaller size, and there's a lot of them, because B is smaller than N. And again, in practice, you can show that it suffices to typically take like 1,000 of these randomly. You don't really need all the extra error induced by using random subsamples. It's tiny. We get the quantile, then we get a confidence. So why would this work? Why does this give you, I'm going to give you a kind of heuristic for why this works. The actual proof, by the way, is not so difficult. And, if you want to look it up, it's in a book by Romano and Paulides. The book is, not surprisingly, called Subsampler, which has, by the way, lots of interesting stuff because it shows you how to extend time series problems and spatial problems and so on. But the basic proof that this works is only about page and a half long. And it doesn't involve any various seam theorems or any complicated calculation. And it really works like this. I'll just kind of outline the heuristics. The proof, which is the following. Let's look at this thing. First of all, let's decompose this term and write it as root B. I'm going to add and subtract the true value. So all I did there was I just add and subtract that. So this is looking good. That's looking like something. How about this term? This is kind of weird. This is theta. This is computed from the original data set of size n. This is root b. But let's now multiply and divide here by n. So this is actually root b and is root n. Well, what do we know about this? This is converted by assumption. This is converting a distribution to something, right? We don't know what it is, but it's converting a distribution to something. If it's converging in distribution to something, it's bounded. It's bounded in probability. It's OP1. It's not taking off this thing. But how about this term? This term, we assume this is where the assumption that b is less than n. b over n is going to 0 by assumption. So this term is going to 0. So in other words, I can replace this approximately now. I'm just going to replace it with theta because there's an error term size. If you want to keep track of error terms and the size of the error terms. Now what do we do with this thing? This is theta hat j minus the true value times root b. This is an empirical thing. Well, it turns out that there's a true distribution here, which is, I'm going to call it LBT, which is the probability that if I took a sample of size, so this is going to represent kind of a generic sample of size B, let's call it. What is this thing really estimating? It's estimating the estimator, but not the original estimator, an estimator based on sample size B instead of n. And it's really kind of, this is like an empirical version of this estimator. In fact, we can say very precisely how close these are using concentration of measure. It turns out this is not quite like the concentration of measure we've done before. This is actually something called a U statistic. It's like it doesn't matter. Let me just tell you that the probability that this is, say, bigger than epsilon, but if you go back, here's an interesting fact. If you go back to Hoofding's original paper about his inequality, it wasn't about means. It was about very general quantities. This isn't quite a mean because it's involving subsamples. But Hoofding's original paper actually covered this case. And what do you get when you're subsampling? Instead of getting minus 2n epsilon squared like we did in Hoofding's inequality, you get 2n over b. So from Hoofding's inequality, we're getting that this is very close to this probability. In fact, the error you can see is of order, this is also of order. The difference between this empirical thing we're teaching and the theoretical one is of order, again, d over n, which is going to 0 by assumption. But to construct a confidence interval, what I really need this distribution. That's the original thing I want. This is almost the same thing, but it's based on the idea of using subsamples of size b. I really want, let's call it now n. So what's missing here is I've got this empirical thing which is very close to this. I've got that L hat is very close to, let's call it L sub b plus error. But what I really want to make a confidence interval, remember, is the oracle distribution, this thing. But if I add and subtract that, this is the thing I want. This is going to 0. But look at this. I have LB minus LN. I have the distributions. This is the distribution of my estimator from subsamples of size B. This is the distribution of size S. But remember, the other assumption is that B is going to infinity somewhere. That is the other assumption. So far, we've been using the assumption that B is going to 0. B over n is going to 0. If B was fixed, we'd be in trouble because this is going to converge to some limiting distribution in this would. But if B is going to infinity and n is going to, they're both going to the same limiting distribution. So this is also going to be 0. In fact, typically it's going to be of order 1 over mu b. But that doesn't matter. So this is going, so this difference is going to 0. This is, sorry, this is the wrong one. LB minus L is going to 0. We conclude that this empirical thing is approximating exactly what we want. And hence the quantiles from the subsampling distribution approximate the quantiles of this, and therefore we get a valid, asymptotically valid confidence interval. And the only theory that's used in here, really, making this what I just said precise is actually very easy. It's just this thing about Hoofding's inequality, the unusual version of Hoofding's inequality is a little bit small. It's no point, but not that complicated. So again, to run through the details, you can check out their papers and their book, and you'll see it's really only a page and a half long. It's really beautiful that it's so much simpler than Bootstrap. So the advantages of subsampling, again, are even when things don't converge to Gaussians or nice things, it works. It can be extended very easily to non-standard situations like time series, spatial things. There's two disadvantages to subsampling. One is that the confidence intervals, as it turns out, tend to be a little bit wider, and that kind of makes sense because you're doing all the sampling with these subsamples of size B, which are smaller samples, so you're going to get more variability. But then there's this question of how do I actually pick B? All I know about B is that B over n has to go to 0, and it has to go to infinity. So unfortunately, there's a tuning parameter. And I have to admit I'm not too up on this. There's been some papers about trying to use the data to find a good value of B in some sense, and I don't really know enough about them to say how successful they are. But this is probably the biggest reason why people don't use subsampling. They're sort of like, well, how do I actually pick B? And I think common choices are to pick B, like I've seen root n and I've seen n with 3/4. But it does affect the answer, the choice of the subsample size. So that's the disadvantage. But there is a large literature on this, and there may be some good papers about how to do it in a practical way, but I can't tell this on. So this is the bootstrap of this, and a lot of people on ML don't know about. Subsampling, I think a lot of people in statistics don't even know about. It's much less popular. Hopefully, again, I did that off the top of my head, so I'm not guaranteeing everything there is 100% correct, but I think it's morally correct. Any questions about that? Right.
It seems kind of odd to say that you can use the data to prove B, because whatever you do, you have to prove that your rule, which is a random rule, yields a B, a value of B that satisfies those conditions, right?
Yes, well, that's why the papers are involved in animal papers. But I think there are methods that are data-driven in which you can prove theorems about. How well they work in practice, I don't know. But there are lots of papers that, in fact, quite a lot of guys about how to choose. Anytime I've done it, I have to admit, I just arbitrarily said B. I think it was either the end of the 3/4 or something like that. Just because I didn't know what else to do. It seemed to work okay, so I kind of rule of thumb, but they're ready to go. Any other questions? Okay, so one more thing, but maybe that's enough for one day. Let me just say quickly that if you want, I was going to mention that you want to do the bootstrap or infinitely many parameters. So that's a little bit like when you did things for finitely many classifiers and then remove infinitely many. We had to go to things like DC dimension, cover numbers. It's a similar thing for the bootstrap. It involves something. The main reason why I wanted to mention it was just because I talked at one point in the course. Remember, I talked about something called the bracketing number of class of functions, which is how many pairs of functions it takes to cover the space in the function of epsilon. And it turns out that's critical to all this. That if you have a set of if you want to estimate the mean of a set of functions, the bootstrap works if it only has the bracketing numbers not too big. Roughly speaking, if you ever take some sort of course on empirical processes, you'll hear about the word. You hear the word Donsker. Donsker was a guy, and a class whose size is not too big is called a Donsker class. It's much bigger than these. And it turns out there's a very famous theorem by Everest-Genet in the 90s where he proved that if F is Donsker, then the bootstrap is valid. He proved for infinitely many reasons. And the converse is true. If the bootstrap is valid, F is Donsker. So there's this beautiful probabilistic characterization that connects probability theory and concentration measure and bootstrap all together. And, so I guess I won't go into that but for those of you who are interested in that stuff, you can look it up. So that pretty much covers then all the stuff you wanted to say then about bootstrap and related notions of measuring uncertainty. There's two classes left, which you guys voted that you wanted to have the spotlight, so we'll go all through spotlights, right? That was my joke for the day. Now Ryan's going to talk about things like, what are you going to talk about?
I'm going to talk about Stein's lemma, but we're going to focus on Stein's lemma to prove two specific things. The first is the Stein paradox, we're going to prove the time trade-off of the time lemma. And second, we're going to derive degrees of freedom estimates using time lemma.
Okay, so that should be pretty exciting. And that's it. And don't forget, there's one more homework due in the next week, and your projects due shortly thereafter. And then the course is over. All right, so we'll see you next week.